Greetings, physicists, and welcome back to Chapter 9. You remember a few years ago, or excuse me, a few weeks ago, I know it seems like a long time. You remember a few weeks ago when we talked a little bit about gravity and I said I'd be coming back to it? Well, it is time for us to revisit gravity in a little more detail. Some few hundreds of years ago, Newton contrived his having difficulties with this pen. Law of universal gravitation. Now, the reason that I'm going through the bother and the trouble of actually writing this out so you can see the way that it's written is it's maybe a little important. It's the law of universal gravitation. What that's supposed to mean is that every mass in the universe attracts every other mass in the universe. Now, we already know that greater mass means a stronger attractive force. Obviously, we have a greater weight on the Earth than we do on the moon, because the mass of the Earth is greater than the mass of the moon, right? And that's why there are two masses in the numerator of our gravity equation, which looks something like this. The force of gravity between two objects is minus g, and then m1, m2, over r squared, where r is the distance. Let's say that m1 is the Earth, right? And m2 is the moon. And the distance between them we'll say is r. This equation will tell you exactly how strong the force of gravity is in between these two bodies. Now, let's examine some ways that we could try to manipulate this equation to make a little more sense out of it. Obviously, we have two masses here, and if one of them gets bigger, this whole number gets bigger, right? The greater the masses, the stronger the force of gravity. And so if either one of them increases, so does the force of gravity. This thing here, this capital G, this funny looking capital G, there we go, that's a little better. Capital G is this funny number. G is actually 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Funny unit. Now, you're not going to have to remember that. If you're going to have to do that on an exam, you're going to have to solve one of these on an exam or something, I will obviously give you this. I'm not asking you to memorize it. I just want you to know that it is there, that it exists, and that it is a funny number. So funny that it was so evasive, so difficult to figure out that Newton couldn't even figure it out, and he figured this out, this law of universal gravitation. And it wasn't until about 70 years after he died that we were able to experimentally determine how big this number is, or how small, right? 10 to the minus 11. Now, the unit comes from the fact that this has to be a force, right? So it has to be newtons. But then we're also multiplying all of this here. What we got kilograms squared in the top, so we have to divide by kilograms squared. We got meters squared in the bottom, so we have to multiply by meters squared, so that these will cancel and leave us with newtons, right? That's it. In any case, notice a few of the important things here. The book has omitted one huge detail, and that, of course, is this minus sign, the negative sign. That is very important, because the force of gravity is always attractive, seeking to make the distance between two objects less, never more, right? It is not a repulsive force ever. It always attracts two objects to each other. And that is one of the reasons why sometimes we say that gravity, or surface gravity, is minus 9.81 meters per second squared. If not, if we leave the minus sign off, we just have to remember that it's downward, right? Always seeking to decrease the height or the distance in between the Earth and the object that's falling. Just remember, gravity always accelerates objects towards each other, and the distance must decrease as a result of this attractive force. But the force of gravity also changes sharply with distance, as we can see here by this 1 over r squared factor. What does this mean? Well, I'm just going to rewrite our law of universal gravitation up here in the corner again. Now this 1 over r squared factor, this is going to tell us what's going to happen. Let's say that the moon was all of a sudden twice as far away from the Earth, right? So the distance went from r to 2r. What's going to happen to this equation here then? Well, we got, instead of 1 over r squared, it's 1 over 2r quantity squared, and that's 1 over 4r squared. That's 1/4 what it was before. That means if you double the distance in between two objects, it will decrease the force of gravity by a factor of 4. What would happen if we tripled the distance? R then would become 3r, right? Well, our 1 over r squared becomes 1 over 3r quantity squared. That's 1 over 9r squared. That's 1/9. So if we double the distance between two objects, the force of gravity is cut by a 1/4. If we triple it, it is cut by a 1/9. If we quadruple it, it's cut by a 1/16, and so on. But also, if we halve the distance, if we cut the distance in between two objects in half, then the force of gravity will increase 4 times. If we cut the distance in a third, it'll increase 9 times. If we cut it by a 1/4, it'll increase 16 times, and so on. We call this an inverse square law. Inverse square laws go something like this. If you're planning to divide up whatever force by the square of the distance, then you're using an inverse square law. And you can imagine the force of gravity like a can of paint, right? And if you were to smear this can of paint, this force of gravity, out over a sphere, right, at a distance r from, I don't know, the Earth or something, let's say. So at r, this can of paint is going to cover a sphere, right, with area 4 pi r squared. Now let's just say that r is 1, right? And so essentially, if r is 1, then the area of the sphere is 4 pi. But if the distance is 2r, 4 pi times r squared, 2 times 2 is 4, that's 16 pi. So you've got 4 times as much area in this huge sphere out here that force of gravity is going to be smeared out over. Now I know what you're thinking. Why are we talking about gravity on spheres? Well, that part is actually very simple, because if you're talking about how the force of gravity, or a gravity well, right, the gravitational sphere of influence of some massive body, how is it going to extend its gravity, its gravitational pull out into the universe? Well, it's going to be equal in all directions, right? That's a sphere. And so as this sphere increases, as the distance from this object increases, we can very clearly see that it's still got the same mass. And so whatever force it's going to exert, whatever influence it's going to exert out into the universe at large, obviously it's going to be doing so spherically, right? Every direction equally. And at double the distance, it's going to have 4 times as much area to cover. And so that gravitational influence, the strength of the force of gravity is going to weaken proportionately. Thus, because you've got 4 times as much area at twice the distance, you're going to have 1/4 of the strength of the force of gravity. At 3 times that distance, it'll be a 1/9. At 4 times that distance, it'll be a 1/16, and so on. Now the book goes on to talk about the sensation of weight, even though it had already defined weight as the force of gravity on someone or something, which is correct. But the sensation of weight is not something that you can really measure so much, right? We don't talk about feelings in physics because they're not easily quantifiable. But let's look at it this way. Let's say you're in an elevator, right? So at first, you're in this elevator, and the elevator is not yet moving. Obviously, your weight is pulling you down, right? Gravity is trying to pull you down, and then the floor of the elevator is pushing up on you, the normal force, right? And these are going to cancel each other out. But now, let's say that the elevator accelerates you upward, right? It pulls you up. Now, in that brief moment, while the elevator is going from stop to moving, right? While it's accelerating, what does it feel like? Well, you're going to feel heavier, right? It's going to feel like you have more weight because there's an extra upward force pushing up on you, right? The elevator has to pull you up, and that means you're pushing against the floor of the elevator as the floor of the elevator pushes on you. And this adds to the force of gravity already pushing on you. And so, for that brief moment, while the elevator is accelerating, it's going to feel like you're heavier. Now, if you were standing in this elevator and you were standing on a bathroom scale, right, to measure your weight, while you're accelerating upward, right, because it feels like you're being pushed down into the floor, it's going to read greater than your actual weight, right? But if the elevator is stopped or moving at a constant velocity, right, once it's started moving and keeps going at a constant rate, at that point, the bathroom scale will read your correct weight. Also, while it's slowing down right near the top, you know that feeling while it kind of feels like you're floating just a little bit as you're slowing down? Well, that's because you're accelerating downward, right? Instead of accelerating upward, you're accelerating downward. And so it's going to feel like the floor of the elevator is pushing on you less because you're going to feel like you're pushing on it less, right? And so while it's accelerating downward, while it's slowing down, or if you're at the top and you start to accelerate downward, you're going to feel less than your normal weight. Now, if the unthinkable happens, and the brakes on the elevator fail and the cable snaps, the counterweight starts to fall or whatever, and you and the elevator start to fall, as long as you're falling together, relative to the elevator, you're going to be moving at the same rate, right? You and the elevator are both going to be in free fall. And so relative to the elevator, you're going to feel weightless because the elevator is not pushing on you and you're not pushing on it. And that is why astronauts out in orbit feel perpetually weightless. Because essentially, if you're in orbit, you're in free fall around the planet Earth. We'll come back to that a little bit in chapter 10. In any case, the book also talks about the tides at some length, but it gives it a very goofy, hand-wavy kind of explanation. So let's talk a little bit about the tides, shall we? Let me first reassure you that the tides are a real phenomenon. They do actually exist. Now, we all know that the moon pulls the tides, right? And so here's the Earth. And if the moon is like out here, there's going to be a tidal bulge like this on this axis kind of facing towards the moon. It actually lags a little bit behind it, but that's because of friction. We'll talk about that some other time. But the moon definitely pulls the tides. And what you may not know is that the sun also is responsible for a smaller tidal bulge. Now, there is a tidal bulge on the side of the Earth closer to one of these objects, like the moon, because the gravity here is greater. But there is a tidal bulge on the other side also, because the gravity here is less. And so if you wanted to draw out a vector map showing the difference of forces relative to the center of mass, it's going to be greater here, and it's going to be less here, and that gives rise to this tidal bulge. Now, how long do we take for the solar bulge, the one that's facing the sun? How long does it take for this one to make one complete rotation? Well, that's going to be how long it takes actually for the Earth to go around the sun. That's 365.25 days, what we call a year, right? This one, this tidal bulge that follows the moon, the larger one, how long does it take to go all the way around? Well, that's one lunar cycle, or about 28 days, 1 month, 4 weeks, whatever you want to call it, right? But also something else funny happens during that time. The Earth is going to rotate once every 24 hours. And so while, yes, these tidal bulges follow the sun and the moon, they also have to go through all of our water tables and continents and all kinds of things to get from one place to another. That gives rise to a very funny thing we call tidal heating, right? And it's one of the reasons why we actually have the right amount of warmth here at the surface of the Earth. But I digress. If these two move at different rates, there are going to be some times when they line up on top of each other, and there are going to be some times where they line up perpendicular to each other. In this configuration, when they're perpendicular to each other, they're the lowest, right? Because the water is spread out amongst two tidal bulges. We call this a neap tide. N-E-A-P tide. But let's say that the sun is over here, right? And so both of these tidal bulges should line up on top of each other. And that's when the tides are the highest. We call that a spring tide. Now, what phase of the moon could this possibly happen on? It either has to be where the moon is close to the sun in the sky, or on the opposite side of the sun in the sky. So that's if the moon is opposite the sun in the sky, that's the full moon, and then if it appears close to the sun in the sky, then that's the new moon, right? And then neap tides obviously happen at first and third quarter. Now, why is it that the tidal bulge for the moon is much greater when we know the sun is much more massive, right? Well, the sun is also much, much farther away. And because of the moon's proximity to the Earth, the difference in the force from the near side to the far side is actually greater. The book also talks about the atmosphere having tides. However, that's, while true, it's sort of so far above us that it's pretty inconsequential. The book also talks about tides on the moon, and let me save you the trouble. There are no tides on the moon because there is no ocean and there is no atmosphere. The moon is tidally locked, however, to the Earth. And what we mean by that is that we always see, so here's the Earth, and while the moon is here, we're going to see this face, and sometime later the moon is going to be here, we're going to see this face, and sometime later it's going to be this face, sometime later it's going to be this face, but this face, this face, this face, these are all the same face. this side of the moon always, always faces us. And that's what we mean when we say that the moon is tidally locked. The reason that we think that is that once upon a time, long before there was actually a moon, an object roughly the size of Mars, the Mars-sized impactor, smashed into the Earth and knocked away a chunk of material, and that eventually became the moon. That's sort of been the going thought on it for some time now. There are a couple of holes in this theory, most notably the lack of what we call volatile materials, things that boil at low temperatures. And we would expect to see some of those there because there's an abundance of them on the Earth. But in any case, when this object smashed into the Earth and knocked away a chunk of material which would eventually become the moon, most of what it knocked away had to have been stuff that the Earth was made out of. Now the Earth is actually mostly made out of molten metal, rocks, magma, lava, whatever you want to call it, things like that. And so the moon, if it was indeed part of the Earth originally, that would make sense that all of those things would be in there. Now that's kind of a little funny to think maybe, but if that is true, then there would have been a certain amount of this liquid, hot, molten material, right? Now because metals are dense, right? Metals are heavy. Over the course of time, it is thought that all of these molten metals were pulled closer to the surface by the Earth's gravity, right? By the interaction of Earth's gravity with the moon's gravity. And eventually, when this all lost its heat and cooled off, there was so much mass here, close to the Earth, that this face of the moon, because of the increased density, is always going to face the Earth. And so the heavy stuff essentially keeps one face of the moon locked to us. Say it's tidally locked. A little bit of vocabulary. A gravitational field, like I mentioned earlier, is the region of space-time where an object feels a gravitational attraction to another body. We, the Earth that is, and the other planets are in the gravitational field of the Sun, for example, right? We all revolve about it. The Moon is in our gravitational field because it revolves about us. The Moon is much less affected by the Sun's gravity than ours because it's so much closer to us. Neptune is technically in the Sun's gravitational field, but Neptune and the Earth aren't so much in each other's sphere of gravitational influence, right? Now, if we want to think about the amount of gravity that you would experience below the surface of a planet, and therefore the strength of a gravitational field, first you have to imagine what gravity would be like at the center. So let's talk about if you were down here at the center of the Earth. If you're in the center, there's going to be some mass this way, some mass that way, that way, that way. You're essentially going to have the same gravitational pull in all directions, right? And so at the center of the Earth, basically, you're weightless. Now, if you go out some distance, there's going to be a certain amount of material that's sort of below you, closer to the center of the Earth's mass than you are. And the further out you go, the more mass there's going to be, right? And so the farther away you get from the center of the Earth, the heavier you're going to feel, right? Your mass will not increase, but your weight will, because there's more mass, more and more mass, the further you get away, closer to the center of the Earth's gravity, right? Near its center of mass than you are. Now, if you wanted to express the force of gravity as the function of the distance from the center of the Earth, and we approximate the Earth as being uniform density, which obviously it's not. Most of the metals and the heavy stuff is at the center, and it's lighter and lighter and lighter up until, you know, the crust and the surface where we live. But if you wanted to express the force of gravity as a function of the distance from the center of the Earth, and we assume that the Earth has uniform density, then we can come up with a relation. The mass of material below us depends upon the volume of the material below us, right? How much stuff is in there. Now, the volume of a sphere is 4/3 pi r cubed, right? And the force of gravity, as we said before, is smeared out over a spherical surface. So that's 4 pi r squared. Let's not worry so much. The pi's are going to cancel, you get some numbers or whatever, but we got r cubed over r squared. So essentially, your weight, of the force that you're going to feel as a result of gravity is going to be proportional to the distance, just r cubed over r squared is r, right? Long story short, it's going to increase linearly. So we wanted to draw that. Let's put force on this axis and distance on this axis. It's going to increase until you get to the surface, right? At that point, once you're out here, obviously the greater distance you are, the less it's going to be, right? And so it's going to decrease according to our inverse square law, like we said before. And so it's going to drop off. So in this regime, it's going to go as r. And in this regime, it's 1 over r squared. Now this is just an approximation. This whole thing, Newton's law of universal gravitation, is not how gravity actually works. It's a very good approximation, and it works really well for point masses, two objects that are far enough away from each other they can be considered a single point, like the Earth and the Moon, or the Earth and the Sun, or an asteroid and the Moon, or whatever, right? Works really well for those. But Albert Einstein was able to show that gravity is much more complex, but also fundamentally more simple. If you imagine existence like a big rubber sheet, okay? And if you took a mass, like a bowling ball, and you dropped it into this rubber sheet, it's going to sag, right? It's going to bend. Now imagine that an object rolls into the depression, the sagging that's made by this bowling ball, right? It's going to sag like what we call a Gabriel's horn, like a bent cone, right? And so this sag, if you took a marble and you rolled it into this depression, and if there was no friction in between the rubber sheet and the marble, it could just kind of roll around forever, right? Now in space, there's no friction, right? And so objects basically, when they get caught in a gravity well, like planets around the sun, they just kind of roll around forever. We call that orbit. By the way that the book describes black holes is wrong. And it's true that an object with a fixed mass will definitely have a greater surface area, or excuse me, greater surface gravity if it's smaller, right? However, the book doesn't say why, nor does it have the right numbers. So please disregard. Stars are actually incredibly massive. Our own sun is something like 2 × 10⁻30 kilograms. It's incredibly massive, like 1/3 of a million times more massive than the Earth. And they're only able to stay in equilibrium as a result of them generating a tremendous amount of energy to keep their own gravity sort of at bay. And when stars run out of this energy, when they're no longer able to generate enough energy to keep it in what we call hydrostatic equilibrium, the star's gravity pushing it inward and the energy that it generates, the light, whatever that it gives off, pushing outward. When it can no longer maintain this equilibrium against this intense amount of gravity, the star collapses. Their matter becomes degenerate, which I mean, it's tempted to think that, you know, the matter is going to have to go to juvenile hall or whatever. But what that really means is the matter gets crushed into a configuration that's much, much smaller than normal. Much, much more dense than normal. And the more massive it is, the smaller the stellar remnant or whatever gets left behind when a star dies will be. Stars like our own sun will blow up to become red giants, blow up again to become an asymptotic red giant, and leave behind a tiny little massive object called a white dwarf. A white dwarf is generally very dense. The degenerate carbon that makes up a white dwarf is usually something like 12.5 elephants per coffee mug full. And so if you took, you know, 1 coffee mug full of this degenerate matter, it would have the same mass as 12.5 elephants. Stars that are more massive than that, generally the threshold there's a line that's 1.4 solar masses, and then there's a line that's 3.0 solar masses. Below 1.4 solar masses, you have a white dwarf. In between 1.4 and 3 solar masses, you have a neutron star, which is not just degenerate electrons or electron degenerate, it's also neutron degenerate, hence neutron star. And this stuff is so massive that if you took 1 teaspoonful, it would have the same mass as Mount Everest. And then above 3 solar masses, if you have a stellar remnant that's above 3 solar masses, you have the densest objects in the universe, what we call black holes. And they're of course called that because the escape velocity required to get away from a black hole is greater than or equal to the speed of light. And one of the major caveats to Einstein's theory of relativity is that the speed of light is the ultimate speed limit in the universe, and nothing can go faster than light. Long story short, nothing can escape a black hole, and that's why it's called a black hole. Now, if you're still picturing the rubber sheet, you can picture a black hole as a depression that essentially goes to infinity. Nothing can move fast enough to climb out. Now, the book goes on to fail at describing how it is we detect black holes, and I'm going to pick on the author every possible moment that I can because his grasp of astronomy is not so great. But black holes just so happen to be some of the brightest objects in the universe in the X-ray portion of the electromagnetic spectrum. And if you look up a picture of the electromagnetic spectrum, you'll see that X-ray radiation is very high energy, very short or low wavelength, very high frequency, meaning they oscillate a tremendous amount of times per unit time. And so there's a lot of energy in them, which is why X-rays can go through your skin and into your bones and tell you whether or not they're broken. So the intense gravity of a black hole makes any material that falls into it swirl around it really fast and heat up to a tremendous extent such that it gives off X-ray radiation. The book also butchers the dark matter problem and the dark energy problem. Very briefly, the dark matter problem is we don't know what about 90% of most galaxies is because they don't give off any light, hence dark matter. This was originally found because we were trying to figure out what the velocities were. Let's say you've got a galaxy, here's a core, here's some spiral arms, right? And you would expect that, you know, if there's a bunch of mass here in the middle, that a star here would have a lower velocity than a star, say, here, as they're swirling around, right? But what we found is that's not true. Stars here have about the same velocity as they do there. It doesn't really matter. And the only way that that could possibly be true is if there's a whole lot of matter in here that we just can't see, pulling it around. Hence the dark matter problem. We know probably what about 10% of the matter in most galaxies is. The dark energy problem is that the universe is not only expanding, but the expansion rate of the universe is increasing, and it's increasing at such a rate that we're not really sure about what 63% of the combination of matter and energy in the universe is. That's the dark energy problem. So regardless of whatever you may read in the book, that's what these things actually mean, okay? And if you have any questions, please ask me. I hope you've enjoyed our presentation on Chapter 9 and gravity. I'll see you soon for Chapter 10.